countably additive measures are insensitive to the measurement of rare events. So we need to define these terms. They sound very good, but what do they mean? Let's look at the mathematics. So before I do that, just 1 second. The problem with von Neumann axioms, the mathematical problem, is that they measure the kernel that emerges from its representation theorem, whose von Neumann's, is countably additive, implying that any two lotteries are ranked quite independently of the utility of the outcome in states whose probabilities are lower than sub-threshold level, depending on x and y. This means that expected utility optimization is insensitive to small probability events, no matter how catastrophic they may be. So here we are. We're making decisions based on US law with respect to using expected utility, and this expected utility, I'm telling you, is essentially insensitive to catastrophic events. So we're making decisions which are insensitive to catastrophic events. That's what I said at the beginning. No wonder we have such problems in the United States doing anything that has to do with the environment. No problem the mathematics for planet Earth has to introduce some adjustments. So here go the problem with von Neumann and with the Groot axioms, which, as I said, are completely parallel. I mean, they're just identical theories. Which is that expected utility on the one hand and Gaussian probabilities on the other are insensitive to rare events. So what is insensitivity to a rare event? I need to define that. I'm going to do something interesting. I'm not going to define a rare event. I'm going to define insensitivity to a rare event. And I say that the ranking is insensitive to rare events, where for any two of them, there exists an epsilon that depends on them, x and y, such that I rank the lottery x over the lottery y if I only if I rank any other lottery x prime and 1 prime the same way, where x prime and y prime are obtained by modifying arbitrarily the lottery x and y in a set of state with a small probability epsilon. That's the definition. You can't touch it. Now, as it turns out, this definition here of insensitivity to rare events, A, is satisfied by von Neumann's axioms, is satisfied by Milnor's axioms, is satisfied by Arrow's axioms, is satisfied by all Gaussian distributions, is satisfied by all countably additive measures, is satisfied by all the standard theory. They have that property. That's the next proposition that comes. It's easy to prove. Therefore, what do? I say no. I say axiom. We won't accept insensitivity to rare events. I call that axiom, which is the logical negation, sensitivity to rare events. I introduce that axiom. If there were no rare events, I'm back with von Neumann, with a Groot, with Arrow, with Milnor, we're all friends. But if there are rare events, they got a problem with the rare events. This is it. And I use the logical negation as my axiom, which, by the way, when I started from requiring sensitivity to rare events, I didn't understand how deep this went in the established theory. And now I do. Anyway, a ranking is called insensitive to frequent events when it ignores frequent events. Now you may say, that's crazy. Why are you bothering me with that? Well, I can show you rankings that have that property. Like saying, I'm going to invest your money so that I will maximize what happens in case of a catastrophe. I will take care of you in case of a catastrophe. Okay? Well, that happens to be insensitive to frequent events. So I'm saying no. first of all, I had to convince you that the expected utility and countability probability measures are insensitive to rare events. I don't need to convince you. The proof is very straightforward. But I wrote it there just for the sake. And by the way, easiest for us is for you to ask me, and I send you the presentation. In any case, it's in the computer, so you can.
We will post it on the website.
Yeah. So you have it all. So again, because of this property, which property? What am I talking about? This. That the expected utility, which is for Neumann, de Groot, Milnor, and countability probability measures, which are all the Gaussian measures, are insensitive to rare events. Because of that, I claim that their classic probability measures and expected utility are less well suited for evaluating catastrophic risk, because I'm going to ignore them. So the following is an example that is not sensitive to frequent events, and I mentioned that. That's the example of the portfolio manager, that he will just protect you in case of a catastrophe and forgets about what happens most of the time. So here are the new axioms. Remember that the space of events and the lotteries is L infinity with a subnorm. The axiom 1 is that the ranking of I have to tell you, I have to confess, I keep on changing the numbering of the axioms, so don't get confused. That's the critical axiom. Okay?
No more than 10 minutes.
No more than 10 minutes. The ranking of lotteries is sensitive to rare events. The ranking of lotteries is sensitive to frequent events, and the ranking is continuous and linear. That's it. Those are the three axioms. Axioms 2 and 3 are standard. They are satisfied, for example, by expected utility. Axiom 1 is different and is not satisfied by expected utility. It is the logical negation of the definition that I gave you before. And topology holds the key. Why? Because mathematically, the way, if you look at Milnor's proof of expected utility, Milnor-Hernstein's article, classic article, if you look at arrows, also classic. If you look at von Neumann's, also classic. If you look at de Groot, also classic. They all postulate a form of continuity. And you say, well, sure, when you look at reality, things which are nearby, I see them close by. You have to do that. Otherwise, you have no connection to reality. But continuity is in the eyes of the beholder. Continuity is what topology is all about. If I change a topology, I have a different notion of continuity. Now, isn't that a weird idea? Very strange thing to say. Not quite. Because as I told you before, the parts of the brain that make decisions, the way we think, the way we do physical experiments, the way we look at reality, the way we think about mathematics, without a brain, by the way, you cannot do mathematics. Just a small comment. Therefore, the brain is an important element in making mathematics. But if you look at your brain has different elements. And the part of the amygdala looks at things in a very different way than the cortex. And the amygdala looks at things in a 0-1 way. Actually, it uses the subnorm. While the cortex uses averaging, LP norms, Sobolev norms, and any norm which is an average. While the amygdala is using subnorms. The amygdala is more primitive. The amygdala is from the times that we were reptiles, and is faster, and it dominates, because emotions dominate. I think that's why we still have wars. And it is prepared for survival as follows. If you have a lion coming to us, and is running to you, and you're trying to make a decision what to do, you're not going to start computing the expected utility that it will lead you, and multiplying by the probabilities of different states. You're going to have to make a quick decision. Are you going to run, or are you going to fight? 0-1. That's the amygdala. That's the subnorm. So I don't have a lot of time, but changing the topology, namely the way we measure distances, what's close and what's far, changes our approach to risk, and it leads to new ways to evaluate risk. By the way, all of this has deep mathematical roots, You may say, well, you know, who is going to use L-infinity subnorms in measuring distances? Who? Gerard Debreu. Who is Gerard Debreu? He, with Kenneth Arrow, proved the fundamental theorems of economics, which is Adam Smith, and market and the structure of markets, and in proving Adam Smith's invisible hand theorem, in an article in the Proceedings of the National Academy of Sciences in 1953, Gerard Debreu used a subnorm. And I can tell you why, but I don't have time. But it's fascinating. So the practical implications were not clear, because the interesting thing is that that article by Debreu was introduced to the proceedings, presented and published by von Neumann. I don't know if this is a little bit too high convoluted a joke to tell you here, but von Neumann is undone by the subnorm. And he published Debreu's piece, because he was like a teacher of Debreu, which was based on the subnorm. He didn't understand what was happening there. Anyway, here are the no axioms. If you look at von Neumann's axioms, sensitivity to rare events, sensitivity to frequent events, linearity and continuity in L-infinity. If you look at the no axioms for probability, two parallel theories, they're identical. I'm telling you, any result in one theory is a result in the other. The probabilities are continuous and additive, are sensitive about rare events, and they are sensitive about frequent events. As I said before, I found out, after proving all this, that axiom 2 negates the monotone continuity axiom in Arrow. I'll be pleased to tell you about it, but we don't have time. And the group's axiom is P4, both of which are equivalent to Villegas and Million's continuity axioms, and they all lead to expected utility and to counter-reality probability measures. So the monotone continuity axiom is equivalent to insensitive to rare events. That's a theorem. And our axiom 2 is logical negation. The proof of that is in my article, The Topology of Fear. The representation theorem is important to you, because if I told you everything up to now, you will say, this is a negative presentation about what's wrong with probability and decision theory. And that's not what this presentation is about. This presentation is about, okay, how do we set it right? And we don't have a lot of time, but I tell you, there exist probabilities and decision criteria that satisfy all the three axioms. They are functionals defined by a complex combination of both purely as well as counter-reality measures, with both parts non-zero. This is like a Klein-Millman theorem, because those two are the extremes. And the purely finite reality is Savage, and the counter-reality is von Neumann. Both are there. And we have an example of the functional down there. The corollary is that the second term in that representation, which is in the bottom there, is actually the explanation for the persistent observations of fat tails, and is consistent with general power laws that you see observed all the time in geology and in natural earth systems. And the last theorem here is that the absence of catastrophic events, the probabilities and ranking of lotteries agree with the standard Gaussian probabilities and with the standard theory. This is not a negation, it is an extension of the standard theory. One new result is that you can actually extend these results to finitely many states. So you don't need to look at the line, although it's convenient and it's better to do so, but you can do it also with finite states. There is results in econometrics. I won't bother you with that. They give you necessary and sufficient conditions for doing non-parametric econometrics and the limits of econometrics. There are results to the transition to green economics. Results on how to measure events under uncertainty. And I want to give you, because I'm about to finish right here, examples of the new criteria before you think this is all too mathematical, too theoretical, who cares? Finance. Again, maximize expected returns while minimizing the drop in a portfolio value in case of a market downturn. This is very practical. Inconsistent with von Neumann, inconsistent with Arrow, inconsistent with Milnor, and the perfect example of a criterion that satisfies welfare criterion, choice criterion, decision under uncertainty, that satisfies my three axioms. Network optimization, maximize the expected electricity throughput while minimizing the probability of a blackout, something that is dear to our hearts, particularly after Sandy in New York City. In stochastic systems, the statistics that emerges out of this is jump diffusion processes. I would love to tell you about that. That's the last work I have done. These are references, and it starts with Arrow, the essays in the theory of risk bearing, and then there is a lot of references here of publications that you can read that have developed all of the above. And it goes on, 35 of them. And that's the Herstein article I mentioned, that's the Groot book. And finally, I wanted to thank the supporting institutions for this research and the collaborators, the Air Force of the United States, the Stanford Research Institute in Stanford, California, the Columbia Consortium of Risk Management that I direct in New York City, the Alliance of Small Island States that are very concerned about the catastrophic risk of them going under the warming seas, the Intergovernmental Renewable Energy Organization, le Groupement de Recherche en Économie Quantitative de Aix-Marseille, and the Institute for Advanced International Studies in